Welcome to class 37 for Physics 200. And I don't know, I've been trying to talk about the people who are important to me at St. John's. And certainly, when you think about St. John's, you've got to think about the monastics who play a huge role. So this is Sister Phyllis. H-Y-L-L-I-S, I think. She maybe is more significant to my wife than to me. She was chair of biology when I was chair of physics, so I certainly knew her and recognized her, but she was kind of Ellen's mentor throughout her early part of her career. What you might think of as Dean's optical area, kind of in the western side of the Peter Engel, that was originally geology. And Sister Margaret was the geologist. So there was a geology department that consisted of just her. And so I knew her really quite well. She'd be on our floor, she'd be somebody I would talk to, and I was interested in geology. And I know she was a remarkable person in a lot of ways, as really all of these monastics are. So I'm not sure how all these monastics, the teaching that they do is kind of secondary to their lives. And I think that was maybe particularly true of Margaret. So she loved teaching geology. She was interested in geology. Well, I shouldn't say she loved teaching geology. She loved geology. I think she always had tension that was involved in a classroom of kids who, maybe weren't all that interested in geology. But really, I think what her main interest in, she was basically an artist, a fiber artist. So you see here, after she'd retired, all of this fabric that she was involved with making, and we've got some of her stuff. So I wish I could tell you could visit Sister Margaret, but she died, maybe 5 years ago. So when I came to St. John's, maybe 10% of the faculty were monastics. And all of these people on this page were, people who are in my building every day. So the last remaining one is Sister Jeannie. Sister Jeannie Lust. And I have kind of lots of connections to Jeannie. So it turns out her brother and her sister were physics majors. And so I actually didn't have Lisa in class that I remember. I was on sabbatical. It was her senior year, but she was kind of the top physics major. She now works, she got her PhD, she works for Honeywell, an excellent physicist. And her older brother, I think, was before I came. So Jeannie is the last remaining monastic in these buildings, in the science buildings. So kind of an era is ending. And I think I really want to stress that this is a special part of St. John's, and I think you ought to try and go out of your way to meet some of these incredible people. So I think I've mentioned Wilfred before. So he was a long-term physics prof, and again, his main interests had to do more with the humanities and the history of science than it had to do with physics per se. And he's retired, but he hangs out at the Abbey gift shop that is right off the door to the Great Hall, and he loves to talk to people, particularly physics majors, about kind of what they're up to. So Mel Freund was my long-term colleague in astronomy. So for 30 years, he and I were working together on non-major astronomy, and he was an incredible guy. So again, his major interest, I don't think, was astronomy. So he, I think, was trained as a mathematician, and early on, mathematics astronomy was kind of included in mathematics, basically because it was a statistical discipline as opposed to kind of a physical discipline. But he was really more interested in music, and I think he probably would have liked to have been Bob Koopman, somebody who was organ and piano, as opposed to the monastery sending him off to be a mathematician and astronomer. So Mel has also since died, my colleague of 30 years, who I think of pretty frequently. So Father John, now the abbot, trying to see where my pen is, I guess it's around here, is somebody whose face you should certainly recognize, the face of St. John's. So when I was a young prof here, a bachelor, variety of the bachelor profs, including John, lived in Emmaus Hall. So he just down the block, down a few doors from me in that dorm, and so we'd see him in the television room, go eat lunch and dinner with him. So I feel I know John pretty well, and have so John was a chemist, and a very good chemist, and a very wonderful person. So, I mean, I occasionally hear. So talking about monastics is always tough because of the sexual assault problems with monks, and I guess I'm not sure how exactly to take those stories. So the way that worked from my phenomena is we had a friend who was a monastic, and then suddenly he disappeared, and only later did we recognize that he had been reliably accused, and there was nothing to detect that he was any unusual from any other prof. He's also since died. I won't name his name, but he was a friend, and I'm sure in all areas there's certainly going to be some bad apples. So the concern has been, I guess, that this was facilitated and maybe encouraged a little bit by the superstructure of the Catholic Church. And I can't speak to the past, but I feel I know John, the current abbot, quite well enough to say that this is not something that he would have done and would be now doing. So, of course, the Church is interested in repentance and forgiveness, and maybe that just went too far in these cases, where we now know that these people are often very much like drug addicts, and their best intentions do not pan out in reality. So I'm proud to know John. He's really is a good man, as are all of these monastics, and I guess I'm pointing out John just because he's been in charge during this kind of terrible period, which doesn't relate to his period, but relates to earlier periods in the history of St. John's. I don't know. So this is more than enough said about about these people who were important to me, and I want to stress that I think you ought to go out of your way to meet some of these people. They're incredible people, and get to know them. It's a special opportunity at St. John's. Okay, so what we're talking about here in chapter 31, and we've been kind of muddling our way through it, is kind of a practical aspect. I mean, we've been talking theoretically about Maxwell's equations, but here we're really practical about talking about electrical components, the so-called passive linear two-terminal devices. We've got inductors, we've got resistors, and we've had capacitors. And recently we've been dealing with them separately, but now we've got them all together. And we have this kind of funny story of phasors. which are seemingly kind of a contrived way of dealing with the circuitry by making a physical model of how things work. And we'll talk about that in a second, but it really is exactly what the mathematics looks like at a more advanced level. So one kind of characteristic to keep in mind is that particularly our book, the problems in our book are very commonly dealing with the amplitude. That is to say, how high above or below, right, this distance here would be the amplitude for that wave. And that is not real life. So anytime people are measuring voltages, currents, they're pretty much always talking about the root mean square. And it's very easy to convert between them. There's just this factor of square root of 2 that relates them. So the root mean square level is designed to kind of match up with a corresponding DC value, right? So sometimes the voltage is above the RMS value, sometimes it's below, but it's kind of a typical value which matches up to the DC value. And then we have all of these versions of what I would call Ohm's law, which say that there's a linear relationship between the voltage and the current. And it doesn't matter whether you measure that in RMS values, which is what it's saying here, or you measure them in peak values, right? They're just related by a constant factor. So if one of these equations is true for peaks, then it's also going to be true for the RMS value. So the thing that plays the role of resistance are called reactances, and they depend on frequency. And for capacitors, they have a small reactance at high frequency, whereas inductors have a high impedance at low frequency. So you can imagine if you put those guys together, there'll be some kind of sweet spot where the overall reactance is as small as possible, and so the current is going to be as correspondingly big as possible. So we've got this kind of funny Pythagorean combination of things that is called the impedance, and we're going to note that there's an angle between the current and the voltage, sometimes called the phase angle. And I don't know, we'll talk about this in a second, I guess, when we talk about phasors. And what we're really talking about mostly today, although a lot of what today is just an opportunity to review these devices again, is the power factor. So if you have a circuit that consists of LRs and Cs, the only way that place where energy is actually used up, where it's converted into heat, is in a resistor. So capacitors and inductors are just temporarily storing and releasing energy. They're not going to dissipate any energy. And so the relationship between the overall current and voltage that you have is encapsulated in this so-called power factor, which when the power factor is 1, that is to say when the angle is 0, then the voltage and the current are in phase, and the maximum amount of that voltage times current is being converted into heat. If the angle is plus minus 90 degrees, then we have a pure inductor or capacitor, and no energy is going to be dissipated, the cosine of 90 degrees being 0. And finally, we talked about that sweet spot a second ago where inductors are going to block high frequencies and capacitors are going to block low frequencies. So if you have them together in a circuit, there's going to be kind of an in-between spot where you do the best that you can. And it's called the resonant frequency. And transformers are going to be on to the next chapter after this. Well, same chapter. So I remind you kind of the basic setup. What we have is this Kirchhoff's laws equation. So this is the voltage drop across the inductor, voltage drop across the resistor, voltage drop across the capacitor, where of course this integral is just giving you the total charge. And if we put in the usual choice where we define the peak of current to occur at time equals 0, if we put in that the current is cosine of omega t, then we can kind of get this picture that we'll talk about in a second of putting things together. So if we do this, we were going to have r times I times the cosine of omega t. I should put an I naught there. Right? That's from this equation. And then from the derivative equations, we're going to get 1 over omega c minus omega L times I naught times the sine of omega t. And all of this has to add up to be something that is sinusoidally varying. And what we found was that what we would get is the square root of r squared plus xl minus xc quantity squared times the current times the cosine of omega t with some phase shift. In general, the current and the voltage would not be rising exactly together. And we talked about how to add these things up. So we often called this term the A term and this term the B term. And then what we had in here was of course A squared plus B squared. And this angle here was the tangent of that angle was B over A. So of course, just kind of rearranging this equation, the current that you're going to get depends on the voltage and then this combination of stuff. And we can already recognize what resonance is. The R doesn't depend on frequency, so there's no way we can get rid of that term. But we can get rid of this term if we happen to pick the frequency where those terms cancel, where omega squared is 1 over LC. Then that term will disappear and we'll get the maximum amount of current. And this is the resonance situation. And that's going to crop up more, I think, at the end of this talk as opposed to right here in the beginning. Okay, so here is the phasor picture. So we're going to call the x-axis the real axis because we only care about quantities that are on it. And this other axis, the so-called imaginary axis, is there just to make this geometric construction work. So we're going to put all of these voltages, at least initially, from the origin. So we're going to put the capacitive voltage in the negative y direction and the inductive voltage in the positive y direction. But we're going to be interested in the vector sum of all of these voltages. So here you can see I've moved these things all so they're tip to tail. And what we've got here is the net result, the sum of all of those two voltages, which of course Pythagoras tells us is going to be exactly that combination that we've seen, right? It's going to be the square root of VR squared plus the difference between VL and VC squared. Now, of course, these things are all changing, so we're going to rotate this whole picture by some angle theta. And of course, what's going to happen then is some of the real voltages that we're going to detect is going to be where the red arrow is. And in this particular case, the inductive capacitive pieces are actually subtracting, right? So we're getting a negative contribution. So as a result, the red arrow voltage is less than the voltage by the resistor all by itself. And if we just play the game of what these things are, this whole big distance, that's certainly going to be VR times the cosine of theta. And this piece that we've subtracted from it is given by this piece of it. And that's going to be, I'm just going to call it B, sine of theta. And then the net result for the red arrow is going to be that corresponding quantity. And I remind you, I've got this kind of cheesy demonstration that this whole thing is going to be rotating at the frequency omega, right? So here we have kind of this basic setup. I can change the amount of resistance and hence the resistive voltage. I can change the inductance and hence the voltage that's across the inductor. I can change the voltage across the capacitor. So under these circumstances, the red arrow is leading the resistive arrow, which is the same thing as the current arrow. So we would say that the voltage leads the current. If I have a lot of capacitance, now you can see that the voltage lags the current. So these terms leading and lagging are kind of important. And then what we've seen is that this thing is, the whole shebang is rotating. And so this got to follow the dots. Maybe I'll stop it at some particular point. That's kind of an unusual point to actually have stopped it. But the voltage that you would actually measure is the voltage given by, for the overall system, would be the voltage for this red arrow. So at this particular instant that I've stopped it, there would be very small voltage across the resistor. There would be this voltage across the, I guess that's the inductor, and there would be this relatively big voltage across the capacitor. So at any particular time, I think I can step it. It's making pretty big steps. So again, here is the voltage that you would actually measure across the whole shebang. There'd be this relatively, an opposite sign voltage that's across the resistor, and you could figure out what the voltage is that would be across the inductor and the capacitor. Okay, so the idea is that this is going to be a helpful way of thinking about how these voltages add up. Okay, so let's talk about power. And what we have, if you remember, we have a current that was some amplitude times cosine of omega t, and we had some voltage which consisted of a resistive part that was in phase with the current, and then there was some amount, I'm just going to call it B, could be positive, negative, depending upon the situation, that was due to the combination of the L's and C's. And so this quantity here is the voltage across the resistor. This quantity B is actually the difference in the voltage between the capacitor and the corresponding inductor. So you know, I hope you remember, that the instantaneous power is the current times the voltage. So if I put these things together, what I'm going to get is, just wondering how best to write this. I think I'll leave it the way it is. So I've got this I naught cosine of omega t, and then I've got this combination of, well, I'm going to call it VR times cosine of omega t. And then we've got this B of sine of omega t. So you plug in the time and you would get the corresponding power that would be having to be put in from the overall system. But if we kind of put these pieces together, we're going to have I naught VR times the cosine squared of omega t plus I naught B times the product of cosine omega t and sine of omega t. And if you think about what these graphs look like, cosine is of course always positive, right? So it's going to be looking kind of like that. It has a maximum value of 1, it has a minimum value at 0, and turns out that the average value is a half. So if we take the time average of this term, we're going to get 1/2 I naught, the voltage across the resistor. On the other hand, if we look at this guy, this thing is actually going to be as much positive as negative. So it's going to turn out to have a frequency that is twice as big, but it is just going to have as much positive and negative. And if you kind of think about exactly how this works, if we focus on just the early times, we have the cosine piece, which is going to look like this, and we have the sine piece, which is going to look like this. Ooh, it kind of didn't match things up. But you can see that on this side, we're going to be getting negative contributions because positive times negative is negative, whereas on this side, we're going to get positive contributions, and they're going to exactly cancel because the sign is anti-symmetric to the origin. So the average value of this term is equal to 0 because capacitors and inductors don't actually dissipate any energy. They can store it for a while, but then they have to release it. So this term is going to be sometimes positive when energy is being stored and sometimes negative when it's being released, but on average it's going to be 0. So the average power, which is really pretty much what you're always interested in because typically these AC circuits are, relatively high frequency, not something that you could, many cycles would go in a heartbeat. So you typically would be averaging these guys. So we've said that the average value of cosine is 1/2, and then we would have the peak value of the current and the corresponding voltage across the resistor, which we're interested in actually all of these terms. So I'll write it this way, and I'll also write it the way we could have written it, right, as I squared R, recognizing that this VR is I naught. Okay, but all of these things, all of these currents and voltages, those were the max. And so if we write things in terms of RMS values, this first term would be the RMS current times the RMS voltage. Because the two would go in either way. And the next term would be the RMS current squared times the resistance. Now we can write these things in kind of more generic forms if we want that are sometimes going to be useful. So if we take this form here and remember that the overall voltage, and I'm going to do it as RMS, that's going to be the impedance times the RMS current. So I can rewrite this if I want as the RMS current, the overall RMS voltage, and then what I'm going to have is, I needed to divide this by Z, so I'm going to have R over Z as an overall factor. And this quantity here, that's the power factor. The impedance has to be at least equal to R, so this has to be less than or equal to 1, and of course these things are all positive, so it's going to be, it's not going to go negative, and I hope you can see, well, okay, so these things are all currently being written in terms of voltages, but if we divide out the currents, this quantity here would be the impedance and this thing would just be R. So this quantity is the cosine of that angle phi. And of course, if you want, you can take this one more step. So this is going to be the cosine of phi V RMS squared divided by the total impedance. Okay, so power factor. Another occasion to play around with these kind of generic circuits. So the other topic we want to kind of take up is resonance. So this is a real data that we have for a series LRC circuit, and we wrote down this equation earlier. And as I said at the time, there's nothing I can do about the resistance. That term is always going to be there, but I can make zero this term by choosing to have a frequency that is given by that result. And let me just remind you that this is the actual frequency in hertz. If we bring the 2 pi up, we would get omega 2 pi times the frequency is 1 over the square root of LC. But meters usually don't read the angular frequency, which technically would have the units of radians a second. Okay, so at this end of the circuit, the L is the big reactance thing. So L is the thing that's blocking the signal. At low frequencies, it's the capacitor that's blocking the signal. It has a big impedance since it's 1 over omega. So this is the kind of sweet spot where you kind of do as well as you can do. So when we were talking about these circuits before, we talked about Q, which tells you kind of inversely about the damping. So high Q is small damping, and Q was kind of roughly speaking the number of cycles you would go through before you would, I can show all of this I guess here. So here's the kind of picture we had for just the battery powered case, right? So if I go to high Q, we get lots of oscillations. If I go to low Q, we don't even get any oscillations. This is in contrast to omega, which is kind of determining what the corresponding frequency is. Well, we're interested in the same thing in terms of this resonant behavior. At what frequency do I get a big response? And that's what we mean by the resonant frequency. It's where the current is as big as it can be. If I change omega, all I'm doing is changing the frequency at which this big response occurs. If I'm changing Q, I'm affecting how peaky the result is, right? So small Q, the resonance is spread over lots of frequencies. If we have kind of intermediate Q or we have high Q, we can get the thing to be extremely peaky. It might be worth commenting that if here I'm changing all of Q, if I decided to just change the resistance, just the damping, then not only when I went to high Q, not only would the peak become narrower, it would also become taller. So basically the way this has been parameterized for the purpose of easy display is we're just focusing on the width of the peak as opposed to the height. Okay, so kind of halfway through, I think I've talked about all of the pieces that we want to talk about for this piece. Power factor, resonance, and these are really just applications of what we did the previous time. This phasor diagram that shows us how things combine.